There we go. Okay. So we're going to continue on with ground grid. Tomorrow, it's not supposed to rain, so hopefully that's the case, and everything will be great. We'll go out and do our testing, okay? The testing is really straightforward. So I'll go over briefly. It's a little too light. So we put 4 stakes in the ground. Spaced equally apart. If this is A, this should be 3A. Okay. We inject current. There. So this is I. And there's supposed to be an arrow there, kind of hard to see. And then we measure B across here. Okay. So that's our ground resistivity testing. Okay. You want to test 2 tests. $90 degrees apart. Okay, so if you test in one direction and you're right on top of a cast iron water pipe, that's going to affect your soil resistivity. Okay, so if you check perpendicular to that, then you're not going to see it. Okay, and you'll know that there's something wrong with one of your measurements. Does that make sense? Okay, so drive your stakes into the ground. You'll inject a current, and then you're going to measure. So you've got a current that's flowing from here over to here. Right? And so then you'll have a voltage difference caused by that current, and that's what you're measuring. Does that make sense? Cool. The other test we'll do, we've got ground rod. And then we'll have our voltage probe and our current probe. And now this distance here is what does that have to be, 65 feet? Oh, okay. And again, we're going to have, oh, geez. I don't want that to be a light grain. Okay. So we'll have current going through the ground, and we'll measure, and the ground rod is our common. Okay. So we got to go about 130 feet out with this. It's 65 feet to the voltage stake, and it's another 65 feet to the current stake. Okay. The meter will give you the resistance directly. You'll have some calculations to do for the ground resistivity test. Okay? That make sense? Okay. Beautiful. Okay. So you're going to work in teams of two. Use your data sheet. You want to draw a basic map of where you did the testing, right? This is what you would do on the job, actually. If you do your tests, you get back to the office and you see that something's not right, you can go get some more information on the area that you did your test. And if you've got a map saying, okay, this is where I ran my tests, and you can look at underground structures or whatever and see, based on where you did your test, if there's a problem. Does that make sense? Also, if you want to be able to repeat this test, you want to be able to go out there and know where things are. Okay? Pretty straightforward. Everyone got the first page right on the exam, by the way. Just that I've been, uh, wasn't able to finish it. Okay. So FEA stands for finite element analysis. Okay. Some of the design requirements, if we look at the National Electric Code, um, if we're looking at residential and commercial buildings, let's see if Jake shows up. Okay. So if we're looking at that, it's got to be 25 ohms or less. Chemical plants, uh, 3 ohms or less. Computer data centers, like Google and stuff like that, 1 ohm or less. high-speed material handling. Now, why would high-speed material handling be different? What's going to happen when you're doing high-speed material handling? You're going to build up static charges, right? So does that make sense? Okay. We also have the NESC. That's a National Electric Safety Code. This is what utilities have to abide by. So if you've got a transmission line tower, it's got to be grounded, and that ground has to be 20 ohms or less. Five ohms for small substations. Uh, 1.5 to 5 ohms for or less for distribution substations. One ohm or less for large substations. And generating substations. So it makes sense? So when they're designing a substation, where they're designing a transmission line, they're going to have to come up with the appropriate grounding for the towers, for every one of the towers. And then you've got to test that to make sure that it's the right, it's the required resistance or less. Does that make sense? So if we look at the ground mat, we're gonna have soil. And then we're gonna put the ground mat down. And then we're gonna put gravel on top. Okay. So we have to look at what size conductor we need to have in this ground grid and how fine the mesh is. Okay. Again, we're going to use a computer program for this. So on the extreme, if you've got high resistivity, you might have to use a sheet of copper. Instead of having a ground grid with conductors that are spaced, you might have to use a sheet of copper. For example, the chemistry building at Michigan Tech, the ground grid under the chemistry building is a solid sheet of copper. Okay, because it's basically built on a rock. Okay, a couple things that we want to look for, something called step potential. So So basically, this is the voltage between your feet. If you look at the ground mat, you might have a current coming in, strikes right there. It's going to go out in different directions. Okay. So along that copper rod, you could have, let's say, 62 Ka. Even though the resistivity of that rod is very low, excuse me, yeah, the resistivity of the rod or the resistance of this cable, there is going to be a voltage difference. Okay. So along this rod, there's going to be a kV per foot or kV per meter voltage. All right. Let's just assume, again, you need a computer program for this, but assume a 100 kV per foot voltage. Your step distance, well, it depends on how tall you are, but it's either 2 to 3 feet, right? That implies what? 20 to 30 kV between your feet. Okay. So if you see a fault's about to occur, keep your feet close together, right? You don't want to have your feet wide apart because there'll be a voltage difference between your feet. Does that make sense? The next one that we have to worry about is what's called touch potential. And that's the voltage between your hand or other exposed body part and your feet. So again, we've got, here's your surface. We've got our ground mat. We've got a piece of equipment. That. And we've got a person. So when you touch something, what we're looking at is, oh, and then there's going to be a connection between this guy and the ground grid, usually. So that's going to be your touch potential. Okay. When we toured the substations for UPCO, what did you notice about, like, let's say the manual, like the disconnects with the manual cranks? What did they have for each one of those? Yeah, they had a metal grid, right? Does that make sense? So again, you have that metal grid that you can stand on, and that metal grid is attached to the device that you're working on. And so that should limit the touch potential. Okay. Both step and touch potential in a large substation would use a very advanced computer program. I'll give you some examples, simple formulas, and then a simple Excel spreadsheet to calculate them. Okay, but realize if you were designing a new substation today, you'd be using these what are called finite element models. The whole idea behind finite element models is they break everything into smaller portions. So when you see, for example, the mechanical engineers showing what the stress is on a member, that's done using a finite element model. So they take little triangles and they figure out the stress on every one of those little triangles. And that's how they get the overall stress on the entire, so they'll have like a different color for the different stresses on that beam when they're twisting it or whatever. Same thing with the ground grid. You can calculate for just little tiny segments of the ground grid what the step potential would be, and then it'll calculate it over the entire ground grid. Okay. So that's why it takes a computer program, because you have this really fine set of triangles that you're calculating the voltage at every one of those triangles. Does that make sense? Okay, so there you go. There's step and touch potential, and those numbers, you can be sure that those numbers, there's going to be a table on the exam where you're going to have to answer, what's the maximum resistance for a driven ground rod at somebody's home. Okay. Like I said, we'll go out tomorrow and test those. It's supposed to be dry. You want to note though that as I was coming to class, I noticed that it was raining pretty heavily, right? So in your reports, make sure you note that it was 24 hours ago, it was raining pretty hard.